Keysight is a leader in both simulation and measurement for high-speed electronics, and it is my pleasure to combine these two areas of expertise in this presentation on power integrity. I am Heidi Barnes, Product Owner for Keysight's PathWave ADS Power Integrity EDA Simulation Software, and my colleague, Kenny Johnson, is Product Owner for Keysight's Infinium Oscilloscope Power Integrity Measurement Solutions. From this presentation, we want to leave you with the key reasons for why there is an increasing need for power integrity, how using simulation to design for power integrity is fast becoming a required engineering skill, and what you need to know for making higher frequency power integrity measurements. Here is an example of why power rail noise is not intuitive and why simulation is needed for power integrity. In the upper left is a picture of the Xilinx ZCU104 evaluation kit, and next to it is a picture of the VCCient power rail EM model. Power travels from the voltage regulator module, VRM, on the top side, down through the middle layers and back up to the top side FPGA. I was sure that the worst-case power rail voltage ripple would be in the graph shown on the bottom left. This is the power rail ripple for 400,000 flip-flops switching at 200 megahertz with 13.5 amps. The graph shows 24 millivolts peak-to-peak ripple on the left axis and 200 milliamps of dynamic current ripple on the right axis. But simulation proved me wrong, and measured data in the graph on the right confirmed that the power rail ripple is actually worse when switching the 400,000 flip-flops at a lower 30 megahertz frequency with only 2.5 amps of average DC current. The voltage ripple almost doubles to 47 millivolts peak to peak, but even more concerning is the dynamic current ripple increases by a factor of 10 to 2 amps at the FPGA pins. This result was not intuitive, and the simulation part of today's presentation will show how to use the frequency domain world of impedance to find worst-case time domain voltage ripple. Signal integrity is the goal, but power integrity is the foundation that links all the margin-eating noise sources together. Here is an example of the complexity of a power delivery network for an autonomous vehicle. Data collection from cameras, radar, sonar, GPS, LiDAR, etc. can easily reach 4 terabytes of data per day that cannot be processed remotely and requires localized processors, DDR memory, SerDes, transmitter and receiver devices, etc., each with their own point-of-load power supplies. Fast DIDT switching loads from these components can react with any inductance in the power delivery path to create voltage noise ripple. Switching converters add to this noise, and the power supply rejection ratio determines how much noise travels between the interconnected web of power delivery. In addition, the amount of allowed ripple continues to decrease as power rail voltages drop below 1 volt to meet low power demands and faster data rates. Clearly, this new field of power integrity is not about DC, but rather it focuses on the fast delivery of power at microwave frequencies. Let me stop here for a moment and explain some of the power delivery network acronyms that can be kind of confusing. A point-of-load POL power supply is typically a switched mode power supply, SMPS, with a buck regulator DC-to-DC converter design that the microprocessor PCB world often calls a voltage regulator module, VRM. All of these terms are often used interchangeably to refer to the source of power. Now, a major source of EMI/EMC failures are caused by the large current transient and voltage ripple on the power rail. Failing an EMI/EMC test at the end of the product design cycle, such as this CISPR conducted emission compliance test shown here, can be costly. Late in the design retrofits with added filters and capacitors can add to manufacturing costs, while full design respins to fix EMI/EMC problems result in product delays with daily lost revenue. It is much better to start simulating early in the design phase to understand and mitigate potential power delivery EMI noise sources. I can't say it enough. power delivery for digital loads is AC, not DC. Here again is an example of how the industry often gets it wrong. This is a typical screenshot of a real-time oscilloscope looking at the voltage on a power rail while the digital load is switching. The yellow trace is the voltage ripples seen on the power rail when the load current, shown in blue, is being switched on and off. The equation in the upper left shows one of the primary causes for voltage ripple. Any inductance in the path times the dynamic dI/dt current will result in a voltage change. To evaluate the voltage ripple on the power rail, most data sheets specify a step load. Here we see how the response to the step load excites a small ripple voltage that decays. But what if our digital load turns on and off and excites the power rail at that ripple frequency? Now we get what is called a forced response. This AC forced response is much bigger than the step response and grows exponentially to a maximum that is determined by the Q or sharpness of the resonance on the power rail. Using the traditional step load response, one might think that the design is passing, but finding the worst case forced excitation can easily result in failures from dropped data bits or worse yet, overvoltage damage to the IC. Now I'm going to use simulation to show how easy it is to gain some practical insights into how power is delivered to high-speed digital loads, and then use this insight to develop a robust three-step power integrity workflow for finding worst-case power rail noise. Power integrity starts with target impedance. Digital loads have a very wide bandwidth of digital frequencies which require the impedance to be controlled so that any dI/dt transient times that impedance will not exceed the maximum voltage ripple. The equation is quite simple. Target impedance equals the delta maximum voltage ripple divided by the delta maximum load transient. Applying this idea of target impedance across a wide band of frequencies to deliver power to the load shows something very interesting. The VRM is not the only source of power. In fact, the VRM looks like a low-pass filter because it only delivers power at low frequencies. At higher frequencies, the VRM control loop cannot keep up and its output impedance acts like an inductor and increases with frequency. This is often called the active inductance of the VRM output. A series RL model can be used to model this low-pass behavior. At the frequency where the VRM stops delivering adequate power, it is then the job of the decoupling capacitors to take over. However, capacitors are not ideal, and at frequencies beyond their self-resonance, they become inductors, and they also stop delivering power to the load. The decoupling capacitors look like a bandpass filter that can be modeled as a simple series of C, R, and L. Finally, at the gigahertz switching frequencies of modern-day digital electronics, it is the job of the package capacitance and on-die capacitance to deliver power. At low frequencies, the package die capacitance does not have enough charge storage to deliver power, but at high frequencies, the impedance drops and acts like a high-pass filter. This high-pass impedance behavior can be modeled as a simple series R and C. Combining these three power sources, low-pass, bandpass, and high-pass together in a schematic and then exciting them with an AC load can result in the big V impedance design versus frequency. The impedance peaks are the result of an inductor resonating with a parallel capacitor, like the VRM inductance with the decoupling capacitor's capacitance, or the decoupling capacitor's inductance with the package capacitance. These resonances can be minimized by optimizing the decoupling to match impedance. To match the VRM inductance, set the total decoupling capacitance C equal to the VRM inductance divided by the target R squared. At the higher frequencies, to match the package capacitance, reduce the PDN inductance until it is equal to the package capacitance times the target resistance or impedance squared. This results in the resonant-free flat impedance design shown in the graph on the right. This very simple estimate for flat matched impedance is based on transmission line theory, where the characteristic impedance Z0 is equal to the square root of L over C. This characteristic impedance is where the inductance and capacitance impedances are equal and the behavior looks like a resistor with voltage and currents in phase and there is no resonance. To really show the benefit of this flat impedance design, simulation can be used to excite these impedance profiles with a dynamic load in the time domain. Here is a PI ecosystem voltage ripple time domain simulation that compares the performance of the big V impedance design in the top left graph versus the flat impedance design in the bottom left. In simulation, it is easy to change the AC sweep that generated these plots to a dynamic transient pulse load to simulate voltage ripple versus time as shown in the graph on the right. The graph shows the dynamic current pulsing on and off versus time at 178 kHz to excite the first impedance peak in the big V design. Then, at the peak of the first frequency, the second resonance is excited with an additional dynamic load at 12 MHz. The resulting excessive voltage ripple shown in red is often called a rogue wave, since the voltage ripple of the two resonances can add together if the two voltage peaks happen at the same time. Now look what happens if the impedance is flat with no resonant peaks. Exciting the flat impedance design with the same dynamic current as before results in the voltage ripple shown in green. Here we see that there is no exponential ringing, but rather a critically damped system with a simple delta IR drop due to the change in current. EDA tools like Keysight's Pathwave ADS make it easy to run these simulations and explore the relationship between controlling the impedance in the frequency domain and the impact on worst-case noise in the time domain. Another benefit to flat impedance design is that it provides bigger design margins. Here is an example of how a simulator can make it easy to do a Monte Carlo analysis of component tolerances to see the impact on a power delivery network with resonances versus a design with flat matched impedance. The impedance variation for the non-flat big V design is significantly larger than the flat impedance design, which will result in a reduction of design margins and more product-to-product performance variations. The key takeaway is that these decreasing design margins will force more and more power integrity designers to engineer a flat impedance design. At DesignCon 2020, I had the pleasure of working with Steve Sandler of Picotest and Jack Carroll of Xilinx to show a practical method for measuring dynamic switching current of an FPGA power rail. The results were better than expected. Not only did it work, but it also showed us how to use simulation to find worst-case noise on a power rail. This three-step power integrity workflow that we use to find worst-case noise on the power rail is now available as a video on YouTube entitled Pathwave ADS Power Integrity Simulation Workflow with PI Pro, and it includes a download link for the ADS ZCU104 example workspace. This DC-AC time domain workflow highlights the importance of using EM simulation to get the PCB parasitics correct and using measured models to ensure accurate ESR and ESL parasitics for the capacitors and behavioral models for the VRM. The first step is the EM simulation of the DC IR drop to ensure that the setup is valid and that the expected voltages are delivered to the load without excessive current densities. Step 2 is the AC analysis to create the impedance versus frequency model for the printed circuit board power delivery network with decoupling capacitors. This model is then exported to the schematic for step 3, transient simulation, to look at the voltage ripple on the power delivery network. Pathwave ADS makes it easy to do this whole workflow from within one tool. The DC setup is copied to an AC setup, and then from the AC simulation, an auto-generated component with all the capacitors is ready for use in a transient schematic simulation of the VRM plus PCB PDN plus load for a full PI ecosystem simulation. This three-step workflow was applied to the Xilinx ZCU-104 evaluation kit and provided the following results. The three-step power integrity workflow identified a resonant impedance peak at 30 MHz, which should correspond to excessive power rail ripple if the dynamic load switches at this frequency. Intuition usually tells us that higher current and faster switching frequencies should cause more voltage noise ripple, but this was not the case when increasing the dynamic load from 30 MHz to 200 MHz on the ZCU-104 board. The plot on the left is the resulting voltage ripple when the impedance peak at 30 MHz is excited by a switching load of 400,000 flip-flops at that frequency. The plot on the right uses the same scale, but now the flip-flops are switching at a higher 200 MHz frequency and pulling more current. Since there is no resonant impedance peak at 200 MHz, the voltage ripple does not grow with the forced excitation, and the voltage ripple is actually less than at 30 MHz. These are the simulation results that predicted the measured results for the ZCU-104 vCCient power rail that I showed you at the beginning of this presentation. The success of this PI ecosystem model to predict the measurement improves our confidence in this model and makes it possible to go where measurement cannot, and one can easily use it to predict voltage noise ripple at any location in the power delivery network. In summary, the three-step power integrity workflow starts with a DC IR drop analysis of the PCB-EM model to provide pass-fail margins based on the asymmetrical tolerances of the VRM and sinks. The DC analysis is then copied to an AC-EM analysis where decoupling capacitors are included for optimizing the impedance versus frequency of the power delivery network. The AC analysis then generates an EM model of the PCB PDN with all of the decoupling capacitors for use in the Step 3 PI ecosystem simulation. The PI ecosystem model with VRM plus PCB PDN plus packaged die can then be run in the frequency domain to find impedance peaks, and then the model can be excited in the time domain with switching loads that correspond to the impedance peaks to find worst-case power rail ripple. Each of these steps can be expanded to add fidelity and optimize the design for performance, cost, and size and weight. Adding DC electrothermal accounts for the dependence of resistance on temperature and can help identify potential reliability problems due to excessive temperatures or identify reduced electrical margins with higher path losses due to the increased resistance. Automated decoupling capacitor optimization with the AC-EM model can quickly identify extraneous capacitors that can be removed and help with capacitor selection to reduce resonant impedance peaks. In the final PI ecosystem simulation, the simple VRM-RL model can be replaced with a switching regulator state space average behavioral model. This higher fidelity VRM model allows for both small signal and large signal ripple to be evaluated and can run in harmonic balance in seconds to minutes instead of the hours that is often required by a typical SPICE transient simulation. Here you can see that a tool like PathWave ADS with PI Pro makes it easy to go from simple simulations for insight and intuition to the more complex simulations for pass-fail predictability and accuracy. If you would like to learn more about power integrity basics, please watch the How to Design for Power Integrity 5-part series on YouTube that Keysight sponsored with industry expert Steve Sandler of Picotest.com. Steve is often heard telling power integrity engineers that PathWave ADS is the only tool that can simulate the end-to-end power integrity ecosystem. Steve Sandler is an expert at power integrity ecosystem simulations, and he does it all in PathWave ADS with PI Pro. Now let's switch to the very important topic of power integrity measurements presented by Keysight expert Kenny Johnson.
Wow, Heidi, thanks for that. That's a pretty compelling pitch here for the importance of power integrity, and I really like the simplification of the design flow. That's really attractive to me. Now we're going to go ahead and we're going to switch gears a little bit. We'll talk about power integrity measurements. You know, one of the takeaways from Heidi's discussion is that if we've done our job well and we've got a well-designed PDN, then this is going to help us maintain stable voltages from DC up to the bandwidth of the switching currents in our system. Now, surprisingly, that can actually be above a gigahertz. But if we've done this right, this is going to help us optimize power consumption. It's going to minimize switching noise. It's going to reduce power supply, reduce jitter, which in today's high-speed digital designs is very, very important. And actually, power supply-induced jitter is one of the biggest sources of jitter in these digital systems. Additionally, it's going to help us minimize our EMI problems. So one of the primary validation tasks of validating our PDN design is measuring power rail quality. I'm going to talk a little bit now about what I see as a pretty common test flow for power integrity. First thing is okay, the board shows up and it lands in front of us, and well, we go through and we disable most things except for the regulators, and we turn them on, and we go around with our multimeter and we double check that the rails are nominally where they're supposed to be. Then once we've done that, we go through our power up and power down sequencing testing. And this is vitally important because a lot of devices have a very specific power up and power down sequence. And we have to follow this, or we can come up in an unknown state, we can damage things, we can have a latch up state. FPGAs, for example, have very specific power up and power down sequences. This sequence testing tends to happen many, many times. I mean, it can be hundreds or thousands of times because we're testing many, many different states. There can be the emergency power down state, or over temp, or user defined, or a hibernate wake up, or so the list goes on. But this testing can be quite time consuming. But once we're convinced that the power sequencing is solid, then we go through and look at power rail quality and current consumption. Now, the current consumption, that can be for things like inrush or energy efficiency for battery devices and things like that. One other thing, though, that I want to make sure we don't overlook is the importance of temperature testing along this timeline also. See, a lot of the parts in our system on our PDN are adversely affected by cold and hot temperatures. At the cold end, inrush limiting devices like the negative temperature coefficient thermistors or electrolytic capacitors are adversely affected by the temperature. The capacitors, for example, the viscosity of the electrolyte increases, and that decreases their capacitance, which reduces their ability to store energy, which makes them less effective at filtering out the ripple and noise. On the other end, at the high end, the power supply efficiency drops as the temperature increases, which means as the power supplies get hotter, they're going to go through and generate more heat, which makes them get hotter and so on. Worst case, you could end up with thermal runaway, but more typical is we're going to realize that we're operating much higher temperatures than we anticipated, and that higher temperature then can decrease the operational lifetime of our product. So returning back to this basic flow, first thing I said was power good. Well, what we do a lot is, since we know the next thing we're going to do is the power sequencing, and we have to go through and hook up a bunch of probes to the power rails anyways, is we kind of skip the multimeter and remove that step. We just hook up our probes, and then we ask our scope. In this case, I'm using an MXR with the built-in DVM, and I just ask the scope. I say, hey, tell me what's the voltage on the various channels that I've got hooked up, and it tells me. And so it just kind of saved me a step, which that's convenient and helpful. Now we go into the power up and power down sequencing. And here's kind of a typical setup that we often see. Here's an example with 8 rails. I assign the 4 most important rails to my analog channels, my other 4 to the digital inputs of my scope, and then I put my scope in infinite persistence so that I can visually see if there's run-to-run variations. And then on my most important signal, I go through and I make use of the mask test capability on the scope, and I build a mask around it. And then I run my power sequencing testing. Well, you can quickly see the shortcomings of this approach. First, the digital channels, there's no analog information. So like that trace there that's second from bottom, you can see how it looks like, well, was that toggling? Did it really toggle like that, or was it slow riser, or was it non-monotonic? We really don't know. So we're probably going to have to run the test again with that on an analog channel. The other thing is that there's no statistics, for timing variations then on run to run with those digital channels. Now with infinite persistence, it's great because we can visually see the run-to-run variations, but there's no count of occurrences. So for example, on channel 4 there, where we see some of the where it turned on late in a couple different ways, we have no idea if that happened 1 time, 4 times, 10 times. There's no count of that. Plus, to go through and understand if we're outside of the specification, say for the delta time between channel 1 and channel 4, we'll have to go place markers. So that's time consuming to manually place the markers. The channel that's got the mask on it, well, that's the way to do it because the mask clearly identifies failures and the mask testing keeps track of the number of passed and failed. And that mask that's generated, well, that represents the specification in our timings or in our sequencing spec. The only real issue is that most scopes only have 1 mask on them. So when we're doing our power up and power down sequencing, we reach for our MXR or EXR 8-channel scopes. So we can throw that same 8-channel example, we can have an analog input on all of them. And those scopes have mask testing on all 8 channels and the ability to automatically generate the mask testing. You just give it the horizontal and vertical tolerance that you want and it automatically generates it. Another time-saving feature. Here's an example then of after running some power sequencing testing on the MXR. And it's nice because with just this screenshot, I've got my 1-page test report. I can see the mask that I used. I can see the data down in the right, which is showing the mask test data, how many waveforms I tested, how many fails I had, if I had any. In the lower left, I've placed automatic delta time measurements on there so I can see what the delta time is and I can gather statistics around that to see statistically how solid my power sequencing is to build confidence. So once we've got the sequencing underway, now it's time to go look at power rail quality. So we've got our converters, right? And we're going to go scrutinize that rail. And we're going to look at that rail and we want to make sure that that rail stays within tolerance under all operating conditions. The temptation is going to be to go grab a regular probe and probe that rail. The probably better idea would be to go grab an application-specific probe like a Keysight power rail probe. Doing something like that, we're going to be much better served. See, a regular probe, most probes have 10-to-1 attenuation. When we're looking at the ripple on a rail, we're measuring millivolt amplitude signals. That's getting divided down by a factor of 10 before it gets to the scope. And then on top of that, scope noise and active probe noise is getting superimposed on that. So what we see is a vague representation of what's really there. The power rail probes on the other side have a 1-to-1 attenuation on them and everything so that we and are very low noise themselves, so that what we see is a more accurate representation of what's really there. You can see by probing in the screenshots there, you can see that when we probed that rail, a regular probe overstated the measurement by 67%. Now, there are 1-to-1 passive probes, but those typically have bandwidths around 20 megahertz, which isn't useful for true PI. That's useful for maybe characterizing just the voltage regulator, but not for the noise that can be bouncing around on the PDN. Now, power rail probes is a very rich subject, and Keysight has many webinars and application notes on this, so I'm not going to dig into it too much there, other than to point out that Keysight invented the power rail probes and their use with oscilloscopes, and these probes are optimized for measuring power rail quality only. They're the lowest noise active probes around, but we're able to do that by just making them kind of a one-trick pony. They only measure power rails. So it's kind of the good and bad of it there. Now you see the 2 models that we've got. We've got a 2 gigahertz and a 6 gigahertz. And those may impress you as being high bandwidth, but it isn't uncommon for there to be localized high-frequency noise in the PDN that can actually end up radiating and polluting the radios in your wireless device. So sometimes you actually need that extreme bandwidth for chasing down your PI problems. Another thing I want to point out about the power rail probes is, if you've ever used probes, you know half the battle sometimes is just making contact with the target. And so Keysight offers two browsers for our power rail probes, a 4 gigahertz and 5 gigahertz handheld browser. And these browsers are sized so that they probe across the end caps of the bypass caps. And so you can see there on the screen that one model will work for 0201 and 0402 packages. The other one will work for 0603 and 0805 packages. Now, in addition to using something like a power rail probe to actually look at the rail quality, we might want to understand a little bit about, well, where's the noise coming from, or what's the effect of that noise on my power rails? Well, that's what this Power Integrity Analysis app, the D9010 POWA, does. It helps us understand power rail noise sources and power rail noise effects. So in the screenshot on the left there, what we've done is we looked at the power rail in kind of a before and after. I'm looking at the power rail and I see some noise on it. I put an FFT on that signal. I saw a spike at a frequency I recognize as being the clock frequency of my digital circuit. And so I say, I bet you some of that noise on the rail is from that digital switching loads on that digital circuit. But how much of that noise? How do I know? Well, by probing those 2 points, I run it through the analysis app and it says, okay, here's your power rail before, the yellow, and here it is after, if you could better isolate it from those switching loads. That might be adjusting the impedance of the PDN, for example. And so it shows me the effects of these noise sources on my power rail. The opposite is true too. In the example on the right, what I've got is I'm looking at a serial data line and I built up an eye diagram and I look at the eye width. And then we say to ourselves something like, well, I know I've got noise in my power rail. How much am I throwing away due to power supply induced jitter? Well, you can run it through the analysis app and it shows you again a before and after. In this case, we went from an eye that was 63 picoseconds to nearly twice as wide at 117 picoseconds. So then I can make an informed decision as to whether I want to buy back some more margin by attacking the source of the noise on my power rails and maybe doing something to my PDN. Another set of analysis applications we have is our D9010 PWRA Power Analysis app. Now what this is a suite of 20 automated measurements for switch mode and linear regulators. So that could be AC to DC converters or DC to DC. The list of measurements is on the right. I'm not going to go through them all, except to point out at the bottom there's some frequency response measurements, which might kind of surprise you because you probably associate that more with something like a network analyzer. But with our EXR and our MXR scopes, we're able to do some frequency response measurements, which just saves a little time in trying to find the network analyzer, making sure it's calibrated and the software's up to date and stuff like that. All of these measurements have a built-in setup wizard that's going to go through and step you through setting up the measurement on the scope, connecting your probes to the target, and any other external hardware that might be necessary to really simplify the measurement. An example of this, let's talk about the frequency domain measurement, the frequency response power supply rejection ratio. Power supply rejection ratio is just a measure of how well the power supply rejects the noise that's on its input from getting on its output. And so to do this with the scope, what we do is we take, in this example, our MXR and two probes. And one probe probes the rail going into the voltage regulator. The other one probes the rail coming out of the voltage regulator. Then we take the output of the built-in waveform generator on the scope and we run that into something like the Picotest line injector, which helps us couple that AC signal on top of the DC rail. Then the wave generator function is controlled by the software and it will step a tone through there. So it'll inject a tone, increment the tone, inject the tone, and it will sweep this across the frequency range that you specify with the number of data points that you specify. And then the scope automatically calculates and presents to you in a tabular form and in a graphical form the power supply rejection ratio. Same kind of procedure for something like the control loop response, where we're checking the stability of the feedback network on our switching regulators. Now let's talk a little bit about current consumption and energy efficiency. So again, our power integrity engineer is going to go scrutinize that power rail, but this time he's looking for current, not voltage. And that could be for things like I said, inrush or current, so we're making sure we're not having any thermal issues, or maybe for energy efficiency or battery life. Then temptation is going to be to go grab that time-tested and familiar clamp-on current probe. We might be better served by grabbing something like the Keysight high-sensitivity current probes. And the reason is because the clamp-on current probes, you're probably familiar with them. They're designed to clamp onto a nice big loop of wire and everything, and their size can be cumbersome with these targets, as well as trying to put on that loop of wire. The other thing is that these probes are affected by thermal drift, and there could be some repeatability errors due to residual magnetism, and so they're just not quite as accurate or repeatable as the high sensitivity current probe, and they certainly don't have the sensitivity or dynamic range as the high sensitivity current probe. Just a little bit here on the high sensitivity current probes. We do have some webinars on this and some application notes and data sheets, but just to explain it to you simply, what it is it's actually a selectable gain differential probe. And so a sense resistor is placed on your target, or inside the probe for that matter. It's got a probe head that you can put these in. And that sense resistor can be anything from 1 milliohm to 1 megaohm. You then tell the scope the value of the resistor. The scope goes through and scales things automatically and presents the data to you. The probe has a minimum current range of 100 nanoamps and a maximum current range well over 100 amps. The maximum current is actually dictated by the power rating of the current sense resistor that you use. The probe itself has a 20,000 to 1 dynamic range, and the way we achieve this is, you'll see in that picture on the left, there's 2 outputs to the probe. So those 2 outputs are sent out simultaneously, one through a low gain path and one through a high gain path, a zoom out and a zoom in path. In this case, we're looking at an IoT device, and in the zoom in we can see the sleep and standby current, and then in the zoom out we can see the inrush or active currents, the larger currents. Now, you can view them both simultaneously, and if you do, you can also do things like math functions that take advantage of both channels, like measuring the area under the curve. If you wanted to understand how many milliamp hours were used for this function, it'll measure the area under the zoomed in curve, and then when the clamp on the probe activated, it knows it must then use the zoom out channel, and it'll go back and forth, stitch it together in the math functions. Now, you don't have to use both channels at the same time. You can actually use, you can hook up one and then toggle in and out. Now, I also talked about temperature testing. Keysight's got a line of temperature probes. These are probes that can go in the chamber, and the 2 probes that I showed you today, the high sensitivity current probe and the power rail probe, can go in the chamber, and that allows you to make measurements down to 55 C or up to 150 C. So in summary, we talked about using the built-in DEVM to look at power good, the value of using the mass testing on every channel for the power sequencing, our preference for power rail probes and the power of our analysis apps, and the preference to use the high sensitivity current probe. Now, Heidi and I also covered a lot of information. We try to compile here just briefly a list of resources. So this is videos and data sheets and things like that if you want to know more, or you can always, of course, reach out to your local Keysight contact and they can put you in touch with the right people. And so I'd like to close by saying thanks for taking the time, and I wish you good luck on whatever you're doing.